I did promise I would do a second demonstration of the Winkler method titration, which is the titration carried out 2 times when we're looking for the BOD of a water sample. Now, I think it's important you don't get the 2 terms confused. The Winkler method is the method of titration used to calculate the amount of dissolved oxygen in a body of water. Okay, the BOD is where you carry out the Winkler method twice. The first time on a sample of water that's been taken, you do it immediately. Then the second time, you do it on a sample of water that has been left in darkness for 5 days at 20 degrees. So when you get a body of water under test, you divide it in 2. You do the Winkler method titration on the first one immediately. You put the second one away for 5 days at 20 degrees in darkness. And after that time, you take it out and you carry out the Winkler titration method again. Both of them will give you a level of oxygen, and depending on what the discrepancy is between the two, the smaller the discrepancy, less demand, less pollution. Greater discrepancy, greater demand for oxygen, greater pollution. That's the link between the two. So let's take a look at this question here, because it gives us an idea as to how the BOD experiment actually works. A sample of polluted water was analysed in order to determine the amount of dissolved oxygen in the water using the Winkler method. The main reactions may be represented as follows. Now, you'll notice there's 2 equations here. Any time in chemistry they give you 2 equations in an experiment, or more equations, there should always be a link. They should be seen as a continuous flow from one to the other. So if we look at the ending of equation 1 and look at the beginning of equation 2, we should notice some overlap, and we do. The manganese oxide here is linked to the manganese oxide here. Now, to make sure that it's seen as a continuous process, we've got to ensure that the coefficients in front of both are the same. So this ends in 2Mn2O3. This one here should begin with 2Mn2O3. So I'm going to put 2 in there, which means that we're going to multiply the entire equation by 2. So that will lead to 4, bring that up to 12. It'll bring that up to 4. It'll bring that to 2, that to 6. You might be wondering, why am I doing that? Because now it's seen as a continuous process right the way through like that, but doesn't it link the oxygen and the iodine? So now it links the oxygen and the iodine, and it tells me what the N1, N2 relationship is between the two of them. So with oxygen and iodine, we can see here straight away it's a 1:2 relationship. Okay. From your previous redox titration involving sodium thiosulfate and iodine, we should also remember, and we have to learn this, that the relationship between iodine and thiosulfate is itself 1:2. So if I was to add the thiosulfate ion in here, the S2O3, 2 minus in here, that would be also 1:2, which would make that 4. So there is a possibility, if you want to try it out yourselves, that you can link the oxygen directly to the thiosulfate through the iodine. However, I think for the purposes of our calculations, we're going to stick with whatever they give us in the question and just use the numbers that we're familiar with. So let's read on. And I'm going to highlight some of the terms as we move along. A 200 centimeters cube sample of water was diluted to 2 litres. And that's extremely important, because that means the answers we get will be 10 times diluted. So we have to bring them back to the original concentration. 200 centimeters cubed of this diluted solution were analysed by the Winkler method, and 22.7 centimeters cubed of 0.01 molar sodium thiosulfate were required. Okay. A second 200 centimeter cube sample stored in the dark, 20 degrees, 5 days. That's standard when you're doing this BOD test. So when you take a sample of water, split it in 2, analyse one immediately by the Winkler method, put the other one away for 5 days in the dark at 20 degrees, and then analyse it by the Winkler method when you're ready to go. So what we noticed? It was analysed then for dissolved oxygen. The liberated iodine, interesting, 4.8 centimeters cubed of 0.01 molar sodium thiosulfate. So it's iodine that's mentioned. Now, reading the 2 paragraphs, there's only 2 chemicals mentioned, sodium thiosulfate and iodine. So we're going to have to carry out the calculation twice. Once on the first paragraph, which was the initial water sample, and then secondly for the water sample that was left in darkness for 5 days at 20 degrees. So we now have established that we're looking at I2 being titrated with S2O3 2 minus, the thiosulfate, and we want V1 M1, N1, and V2, M2, and N2. So we've got 200 centimeters cubed of an unknown molarity containing iodine, and we also then are told that after titration 22.7 centimeters cubed of a 0.01 molar solution was required for the titration procedure. Now, what's N1 and N2? Well, it's iodine and thiosulfate. Iodine and thiosulfate is 2:4, better known as 1:2. So the iodine gets 1 and the thiosulfate gets 2, which now opens up the calculations as 200x is 22.7 times 0.01 all over 2. And that will give me x is equal to 22.7 times 0.01 all over 2 200s, 400. Remember what I told you? Manipulate before you calculate. Don't bother doing any calculations until you've manipulated your formula, and then get your calculator to do the rest for you. So turn on your fraction. 22.7 times 0.01 divided by 400, and the answer there comes out as 5.675 by 10 to the power of -4 moles per litre. Because don't forget, the results of every titration calculation are moles per litre of iodine. Now that's important. We want to know what the concentration of oxygen is in the original sample. So we've got two things to do. First of all, we've got to take the iodine back to oxygen. What's the relationship between iodine and oxygen? It's 2:1. So therefore, 2:1 means we're going to half this in order to work out the concentration of oxygen. So we take that and divide it by 2, and we end up with 2.84 by 10 to the power of -4 moles per litre of O2. Now, second change, I have to go to parts per million. So in order to go to parts per million, the first thing I've got to do is go to grams per litre. And to do that, I'm going to multiply it by the mass of the substance I'm looking at, which is oxygen. 2/16 are 32. So I multiply that by 32, and I get 9.08 by 10 to the -3 grams per litre. But because it's an environmental question and it's a natural level of oxygen in water, we have to turn it into parts per million. So grams must go to milligrams per litre, which means I'm going to multiply by 1,000. And that's going to give me 9.08 milligrams per litre, which is 9.08 parts per million of O2. Alright, so that's the first one. Now, the second one is the one that's been kept in darkness at 20 degrees for 5 days. So we're going to go through that again, and we're going to do exactly the same thing with that as we did with this one here. So I'm just going to write down 9.0, and I'll come back to that in a moment, parts per million. And then I'm going to clear this and do the second calculation. Okay, so the second one then says, a second 200 centimeter cube sample was stored in dark for 20 degrees at 5 days, analysed, and this time we're told 4.8 centimeters cubed. So again, we've got our I2 being titrated against S2O3 2 minus. So that's V1, M1, N1, V2, M2, N2. Okay. Now, V1 again is 200. You've got an unknown molarity, and here, this time, 4.8 centimeters cubed of a 0.01. So the molarity is still the same. And again, because it's iodine with thiosulfate, we remember that this is very much a 1:2 relationship. So 1:2. And again, you have to learn that from the previous redox titration. So we get 200x is equal to 4.8 by 0.01 over 2, which means x is equal to 4.8 by 0.01 over 400. Again, get your calculator out and do it. So 4.8 multiplied by 0.01 divided by 400 equals 1.2 by 10 to the power of -4 moles per litre of iodine. So we've got to do the same thing again here. we've got to go to oxygen, and we've got to go to parts per million. Okay, so if that's moles per litre of iodine, I want to go to moles per litre of oxygen. So hopefully you can remember there was a 2-to-1 relationship. So the amount of oxygen is half that. So we divide that by 2, and we get 6 by 10 to the power of minus 5 moles per litre of oxygen gas. Now I've got to go to parts per million. So first of all, we're going to go to grams per litre by multiplying by the mass of oxygen, O2, which is 32. And when we multiply that by 32, we get 1.92 by 10 to the power of minus 3 grams per litre. And the last thing to do is to go to milligrams per litre. And that's by multiplying by 1,000, because it's 1,000 milligrams in a gram. And when I multiply by 1,000, I end up getting 1.92, which is equal to 1.92 parts per million. Now, one thing I've got to remember, before and after. Before the 5 days at 20 degrees in darkness, and after the 5 days in 20 degrees in darkness. All right, what do we have? The original one was 9.08, and this one was 1.92. However, didn't we dilute the water beforehand? Didn't we dilute the 200 centimeters cubed to 2 liters? And if 200 centimeters cubed is being diluted up to 2 liters, which is 2,000 centimeters cubed, that means that we've got to multiply both of these by 10 in order to bring them back to the original. So this is the diluted one, and I want to go back to the original one. So that means I've got to multiply by 10, which gives me 90.8 parts per million, and this one here gives me 19.2 parts per million. So what's the demand for oxygen? The BOD, the biochemical oxygen demand, is the 90.8 minus the 19.2. So we've got 90.8 minus the 19.2, which is 71.6 parts per million. Quite high, because if you think about it, in the original sample there was 90.8. There's been a demand for well over half of that oxygen, leaving us with only 19.2 parts per million after 5 days. Therefore, my conclusion would simply be the water is polluted. And we can tell that by the demand, the biochemical demand for the oxygen content in that body of water. Now, that's a typical exam question on the Winkler method and the BOD test. So again, remember, the Winkler method is the titration, in which we get the concentration of oxygen. The BOD is when we divide a body of water into 2. We do the Winkler method immediately on 1, and in this case here, we got 90.8 parts per million. Then, after 5 days in darkness at 20 degrees, we take out the second sample, we do the Winkler method again, we got 19.2 parts per million, telling me that over 5 days, there was a demand of 71.6 parts per million by the organic material in there. That's a polluted body of water. So I'm going to leave you with the rest of the questions now. If you go back into Google Classroom and look up the revision sheet that I've given you, I'm going to give you those questions to do. And again, if you have difficulty with any of them, please by email come back to me and I'll send you on the solutions.